Good morning, everyone, and thank you for attending the first opening the talk of the UTIG seminar series for spring 2024. I'm pleased to introduce Professor Steve Constable for this first talk. Steve embarked on his academic journey doing a bachelor in geology at the University of Western Australia, and to continue, he graduated with honors, and to continue the honorable tradition that Damien started the last seminar. This introduction will also not gonna mention any years. So from there, he pursued a PhD, moved to Canberra to do a PhD at the Australian National University. And in that same graduation year, the unknown one, he quickly jumped to Scripps, Institution of Oceanography, for his postdoc, where he never left since, doing a great career over there. So during his career, from PhD rising up to distinguished professorship, let's just say achievements and contribution to electromagnetic methods was substantial, and that kind of reflected with many awards that will take the entire seminar if I will list them, but among them the SCG Award and of course the AGU prestigious fellowship. Steve kind of changed our understanding in a way that we see Earth in tectonic processes and fluid flow, and also one of the first people who did the exploration resource using marine electromagnetic methods by imaging the crust and mantle. He had developed through the career the largest, correct me if I'm wrong, but the largest instrument facility for marine EM. And in terms of mentoring the next generations of EM practitioners, he had more than a dozen, I think now, of PhD students. Among them our own Dallas Sherman. And actually a fun fact, one of his earliest PhD students was briefly my PhD supervisor. So that makes me technically your scientific grandson. Ooh. Sorry for you. And so, yeah, please join me in welcoming Steve and hear his insight from the source about electromagnetic methods and their applications.
Thank you, Eric. It's a pleasure to be here. Let's jump right in. I don't normally give outlines, but it was a good excuse to show this lovely little picture that I scraped off the web. I'll give you an introduction to EM methods, explain what EM induction is anyway, a brief history and the commercial adoption, and then show you a couple of examples of the sort of work that I've been doing over the years. So why electromagnetic methods? The reason is simple. Electrical conductivity varies by more than 5 orders of magnitude over common Earth materials, and if you include minerals such as ore minerals and quartz, it's over 10 orders of magnitude. But more importantly, some conductivity signals are indicative of geological processes that are invisible to seismic methods. So, for example, we can tell freshwater from saltwater, which of course has the same seismic velocity. And you can infer things like partial melt, porosity, temperature, rock type. So there's 2 basic techniques that we're using. The magnetotelluric method uses natural variations in Earth's magnetic field that are associated with the interaction with the solar wind and lightning strikes in the Earth atmosphere cavity. This induces currents in the Earth. So if you measure the magnetic field and the electric field at the surface of the Earth, you can create an impedance that tells you about the electrical conductivity in the Earth. And because you've got this free broadband spectrum of energy, the MT method can actually see quite deeply into the Earth For another talk, I could tell you that I can actually see the Earth's core using this technique. The natural signals can be supplemented by man-made signals, which gives you a little more control and resolution in certain circumstances. The man-made transmitters can either be magnetic signals made by a big loop of wire or electric currents driven into the ground through a dipole. And I like to call these controlled source electromagnetic methods, and quite common for near surface mining exploration. Obviously, with a man-made source, you're going to be limited as to how deep into the earth you can probe. And both of these methods can be used in the marine environment. We can put down electric and magnetic field recorders on instruments and sync them to the seafloor, and use the Earth's magnetotelluric signals. And we can also tow a transmitter close to the seafloor, producing a controlled source man-made signal. The receivers for MT and CSEM are the same beast. It's a recording data logger, couple of magnetic field sensors, and some electrodes that we put on 10-meter arms to make electric field measurements in the seafloor. The yellow thing you see there is a package of glass flotation balls, and underneath the instrument is a concrete anchor. We sync the instrument to the seafloor with the concrete, and then when we're done recording, we send an acoustic signal which lets go of the concrete, and the instrument floats back, and then we capture the data. The transmitter is towed on the end of an oceanographic cable, 50 to 100 meters above the seafloor, the transmitter you're looking at here, we call SUSI, Scripps Undersea Electromagnetic Source Instrument, can put out up to about 400 amps, nominally 500 amp transmitter. Commercial transmitters have been built that put out nearly 10,000 amps, but for most of the sort of work that I do, that's overkill. And the biggest problem is knowing where your instrument is on the end of the cable. And so there's a lot of ancillary navigation equipment bolted onto the system in order to tell that. So just to sort of recap, the magnetotelluric method is fairly simple. You just throw instruments over the side of the ship, wait a few days, and then collect them back. You can see very deeply into the earth. But because the high frequency fields from the magnetosphere get absorbed by the conductive seawater, we have limited resolution in the near seafloor geology, which can be compensated for by using the CSEM method, where we tow our own source of energy close to the seafloor, where it doesn't get absorbed by the seawater, it couples directly to the seafloor, and that improves our resolution throughout the crust and even into the upper mantle if you take time to stack up and use a big current. On the other hand, the vessel requirements are a little more complicated. It's not a matter of just throwing instruments over the side. You now need a winch and a cable. We started getting interested in gas hydrate, where the region of interest is the top 500, maybe 1,000 meters of the seafloor. And so we modified the CSEM method to produce higher resolution in the very near seafloor by towing receivers behind the transmitter rather than deploying them on the seafloor. If we deploy them on the seafloor, we can actually get source receiver separations of up to 100 kilometers, which we'll see into the mantle. But for very short source receiver offsets, it's a cumbersome process to deploy the instruments. So towing them behind the transmitter at spacings of 200 meters out to a kilometer or so works much more efficiently for near seafloor work. And then when I was asked to get involved in looking at permafrost in the shallow water off Prudhoe Bay, I realized the solution was to produce this continuously towed system on floating instruments on the surface. And we call this system the porpoise system. and it produces similar resolution to the Vulcan system in shallow water. And now you can deploy the system off a really small, inexpensive fishing type vessel. So I'll show you examples from all these methods. But first, what is electromagnetic induction anyway? So a geologist colleague once challenged me to explain to a geologist how EM induction works. And this is the best I could come up with. It all starts with a time-varying magnetic field, whether that's the natural variations in Earth's magnetic field or some frequency being transmitted from a man-made controlled source system. And Faraday's law says that if you've got a time-varying magnetic flux, it's going to produce a circulating electric field. Now, in free space, this produces electromagnetic radiation. But if you're inside the Earth, where you've got conducting fluids, minerals, Ohm's law says that that electric field will generate an electric current. And then Ampere's law says that an electric current is going to produce a circulating magnetic field. And this is a secondary magnetic field. And because of the sign in Faraday's law, the minus sign in Faraday's law says that that secondary magnetic field is trying to attenuate the time variations in the primary magnetic field. It tries to damp them out. So it serves to attenuate the variations in the primary magnetic field. I won't make you suffer through vector calculus, but you can show that the electric and magnetic fields generated this way are governed by the diffusion equation. And when we think of diffusion equation, we think of heat flow, which is perhaps the most lowest resolution geophysical tool there is. It's not as bad as heat flow because we get to control the time derivative of the field by choosing the frequencies. And so I was at the AGU meeting last year, and I met Betty Johnson, who used to work at Unical and Chevron back when we were first starting to do industry applications of marine EM. And she very nicely said that she still has this slide pinned up on her wall. I mean, people, when we first started this business, people would say, well, what is the resolution of EM methods? And the answer is it lies somewhere between the resolution of the seismic method and the resolution of potential field methods. And it's all through this issue of the time derivatives. So in the top equation, we have the wave equation for ground penetrating radar, which operates at megahertz frequencies. And that allows the second derivative to compensate for the fact that the electrical conductivity, which shows up in the first derivative term, sigma, is many, many orders of magnitude bigger than the electric permittivity, which shows up in the second derivative term. And to the right there, you see the seismic wave equation with the loss term included, and it's the same equation. And for wave equation methods, the resolution is basically comparable to the wavelength you use. But while the seismologists can push waves all the way through the Earth, the loss term in the radar equation means that the fields get attenuated within tens of meters of the surface in ground penetrating radar. When you go to the lower frequencies that can propagate more deeply in the Earth, basically we work at around 1 hertz plus or minus a few orders of magnitude. The second derivative term becomes essentially 0, and we have this diffusion equation, which is the same as the heat flow equation. But it gets worse if we go to 0 frequency, as you would for DC resistivity. We reduce the equation to Laplace's equation, and with all due respects for the potential field people in the room, the resolution of the potential field method is bounds only. You can put bounds on depth and you can put bounds on size, but it has very poor intrinsic resolution. So here we are, we're sitting somewhere between seismics and gravity. So here's what those electric and magnetic fields would look like in a uniform conductor at a single frequency, and they're falling off exponentially with depth, and the characteristic length scale for that is called the skin depth, and is about 0.5 kilometer times the square root of the resistivity times the period. And the induced electric fields are 45 degrees out of phase with the magnetic field. And if we take the ratio of the electric to the magnetic field at the surface and normalize by frequency, we get an estimate of what the resistivity of the ground is. And we call that the magnetotelluric impedance or apparent resistivity. And we can also compute the phase difference between the electric and magnetic field, which for a uniform Earth is going to be 45 degrees at all frequencies. So we calculate the apparent resistivity as a function of frequency. And here's the magic. If we add some change in resistivity at depth, if we add a conductive layer at depth, the electric fields on the surface change, and the apparent resistivity changes, and the phase difference changes, and can tell us about what's going on. And the same thing, if we add a resistive layer at depth, the electric field at the surface gets bigger, and the apparent resistivity gets bigger, and the phase changes. And so this is how we probe the insides of the Earth using this method. For controlled source, it's the same physics, but things look more complicated because we don't have a uniform field coming out of the sky. We have a three-dimensional man-made field, and it gets more complicated, but it's the same business. The amplitude and the phase tells you what the geological structure is under the seafloor. And so this is the workflow. We start with some time series measurements of electric and magnetic fields. They could be the magnetotelluric signals generated by the magnetosphere, or they could be discrete frequency CSEM signals generated by people. And we convert those into, we process those up into response functions as a function of frequency and position. It's essentially amplitude and phase for both MT and CSEM, but in MT we represent it as apparent resistivity and phase, and for CSEM we usually look at amplitude and phase as a function of position for a given frequency. And then we use geophysical inversion to turn those processed data into a resistivity or conductivity image of the Earth. In this case, we're looking at some upwelling underneath a mid-ocean ridge. The red is magma. And then the next step is to use data from laboratory measurements or rock physics models to turn resistivities into something that's useful geologically, whether that's melt fraction, water salinity, porosity, temperature, gas fraction, gas hydrate fraction, whatever you're interested in. So, some history. In geophysics, it always seems that the theoreticians come up with the ideas before anybody starts building instruments and making measurements. Louis Cagniard is famous for proposing the magnetotelluric method in his 1953 geophysics paper. And even then, he suggested that you could make the measurements on the seafloor. Although, if you read his paper, you realize he had no idea what the conditions would be like. He said it would be relatively simple to make measurements of the electric field on a ship moving in the waves, and he's quite wrong. As far as I can tell, Peter Bannister's paper in the same journal, Geophysics, from 1968, is the first proposal to look at seafloor conductivity using what we now would call the dipole-dipole CSEM method. He was working for the US Navy Underwater Sound Laboratory, and the Navy has an interest in what the seafloor conductivity is because it's all part of looking for submarines and mines and so on. The practical application dates to the 1980s and 60s from my predecessors at Scripps, Charles Chipcox, who bought me out as a postdoc, and his ex-student, Jean Fieu, pioneered the actual measurement of deep water magnetotellurics and CSEM. Chip's funding came from the US military. DARPA was interested in pushing electromagnetic communication signals through the seafloor, wanted to know what the seafloor resistivity was. The Office of Naval Research was also interested in noise signals associated with their submarine detection and so on. Interestingly, the Navy is still interested in both of these subjects, and I'm still working with them on that. Most remarkably, only 2 years after making the first CSEM measurements over a mid-ocean ridge, Chip proposed CSEM methods for oil exploration to ExxonMobil. No, Exxon in those days. And when Chip died, I went through his office to make sure nothing was lost. And I came across this original proposal that he'd written. And in it, he explicitly suggests the idea of direct detection of hydrocarbons. And he's got this hand-drawn figure where he's got what I now call the canonical model for 100 meters of oil, 100 ohm meters buried a kilometer deep in the seafloor. And he shows by calculation that there'll be a response with and without the oil field. Of course, Exxon turned him down. He was years before his time. But we, Scripps did obtain some funding from industry in 1984 to develop CSEM methods. It was tied to high oil prices. And as soon as the oil prices went down in 1986, we lost our funding. But interest was renewed in 95 as the industry started working in deeper water. And this was made possible by the tension leg platform that allowed oil and gas production from water as much as 1,500 meters deep. And so industry started working in the deep water Gulf of Mexico. And the blue line here is the number of wells drilled over 1,000 meters in the Gulf of Mexico as a function of year. And the cost of drilling was consequently going up. In those days, maybe $100 million a well, much more than that now. And so the high cost encouraged industry to look at methods to de-risk drilling, and they got so desperate they actually considered EM methods. And so they started funding us mainly to develop marine magnetotellurics to find the base of salt in the Gulf of Mexico, which in those days was difficult to do with seismic methods. And MT moved to CSEM around the turn of the century when Statoil and Exxon both rediscovered the idea that you could directly detect hydrocarbons using CSEM data. So the first project was carried out at the Girasol known reservoir, Girasol offshore Angola, done in November 2000 by Statoil, using Scripps instruments and the Southampton EM transmitter. At the time, Chip's first CSEM transmitter was decommissioned, and I had not yet built one of my own. But my colleague Martin Sinner and Lucy McGregor in Southampton had built a transmitter based on the Scripps design, and so we used that. And we got the expected signals, increased size for the electric field over the surface of the resistive reservoir, because remember, it's the conductors that attenuate the field. So if you put a resistor in the system, the fields are bigger than they would otherwise be. And then not long after that, ExxonMobil did two data collection exercises in the same area offshore Angola. Being ExxonMobil, they won't tell you where they were. But importantly, they had funded me to design and build a new generation of instruments. And so although it was barely more than a year after the first Statoil project, we were using 30 new instruments that I'd built for ExxonMobil. And in the top, you see one survey. So Exxon's approach was to use Greg Newman's three-dimensional forward modeling code to predict the fields that they expected to see with and without the reservoir. So on the top, we have a known discovery. The solid red line and the black dots, which are the data, are the model for an oil reservoir. and the red broken line is the model without the reservoir. And there was a reservoir. We already knew that. And you can see that the data fall very nicely on the prediction for the reservoir. And then they also did a survey over a prospect prior to drilling, which of course is, I wrote a paper with the title, and the geophysicist replied, "Which model do you want?" Exploration managers are notoriously distrustful of geophysicists because we keep giving them any number of non-unique solutions. And so in order to build the trust, the idea was to collect data before drilling. And this was a stacked prospect of reservoirs, Oligocene and Miocene. The red line is for both the Oligocene and Miocene charged with oil. The green line is just the Oligocene, and the green line, yeah, and the blue line is brine filled. And you can see the data very nicely fit the brine filled reservoir prediction. Well, Exxon could have saved themselves $100 million, but of course they did not. They drilled anyway because they don't trust the geophysicists. And it was a dry hole. It was exactly as we predicted. It was perfect example of how EM can save you money if you wish to do so. So why did they drill anyway? Well, the seismologist told them there was a lovely reservoir there. And that's because a small amount of gas will change the seismic velocities quite a lot. So this concept of fizz gas, where you get a few bubbles in the pore space, changes the seismic velocity, you get a nice reflection, you get a nice AVO, and you think you've got yourself a nice oil field. But for electrical conductivity, you don't change things until you've displaced more of the pore fraction. So it takes a lot more gas or oil to change the resistivity. Okay, I'll push on. So this means that CSEM is a useful tool for assessing targets identified by seismics prior to drilling. And this encouraged industry a lot. By the end of the year, there were 3 companies offering marine MT and CSEM as a commercial project. And it even got to the point where custom-made commercial vessels were built to carry out EM surveys. And it works. Well, worked. You know, there's always the possibility of a false positive. A coal seam is a resistor and, you know, can look like an oil field. But the fact is that without an electromagnetic signature, there's very little chance that you've got a commercially viable hydrocarbon prospect. And so this is a compilation put together by Johnny Hesthammer, and it basically shows that there are, you know, almost no commercially viable false negatives, even if there's the odd false positive. But industry wants to drill anyway. They might have a lease contract. They might want to just know what the rocks look like. They may just believe in seismology. And saving money isn't quite the same as making money. And today, fracking and the pressure from climate change to reduce hydrocarbon usage has reduced the interest in deep water exploration quite a bit. So there's still some commercial deep water CSEM being carried out, but not as much as they used to be. But by working with industry, Scripps was able to build up a state-of-the-art instrument fleet. So by taking sponsorship money and renting equipment out, I was able to build up a fleet of about 50 instruments and 2 CSEM transmitters. And then Schlumberger decided that they weren't making enough money from marine EM, and they stood their fleet down in 2015. And after a couple of years of haggling and negotiation, I convinced them to donate it to Scripps. And so now we have a fleet of around 120 seafloor receivers that we can use for all manner of academic exploration, academic science. So let's look at some of that. And speaking of resource exploration, we were funded by BHP to collect data over the Scarborough gas field off the northwest shelf of Australia. This is a challenging target because the gas reservoir is sitting in between a sort of moderately resistive siltstone, the Gurley, and a resistive basement in the Mungroo. So it's a resistor sandwich between two resistors, and it has a big electromagnetic signature, but getting the image of the reservoir through inversion can be quite a challenging thing. But here's an example of a joint inversion of the magnetotelluric and CSEM fields that quite clearly shows the reservoir. But resources aren't limited to oil and gas, and in the new energy technology business, we can also look at geothermal and submarine massive sulfide exploration. On the left there is a nice CSEM image in the Gulf of California over a offshore geothermal prospect. And on the right is the bathymetry and the vertical electric field associated with a hydrothermal vent submarine massive sulfide complex in the Okinawa Trough. So the electric field there is self-potential. It produces a nice signature. We did collect some rudimentary CSEM data, which we're still working on inverting. We got interested in gas hydrate. Karen Weidemeyer, who Eric had mentioned, came to work with me as a student, and I asked her what she'd like to do, and she'd done some work as an undergraduate with Bruce Buffett. And so she said, I'd like to work in gas hydrate. And I sort of looked around and I thought, yes, it's time we started getting into this business. So gas hydrate is, I know there's a lot of you here working in gas hydrate. It's a frozen mixture of gas and water under cold temperature and high pressure. The gas is usually methane, but can contain other gases as well. It's created near the seafloor where the temperatures are cold enough and the pressures are high enough to produce this interesting substance. But the geothermal gradient will take it out of its stability field at a few hundred meters deep in the seafloor. And this edge of the stability field where solid gas hydrate is stable above and free gas is stable below produces this characteristic seismic reflection called the bottom simulating reflector. And it follows the bottom because the geothermal gradient follows the bottom. And so this stuff can be literally set on fire. It's incredibly important. A large part of the Earth's carbon budget is wrapped up in gas hydrate. It's a habitat for life. It may have impact on climate change if it's destabilized in shallow water. It's been implicated in submarine landslides, which would imply tsunamis and infrastructure damage. The Storjega slide off Norway is one of the biggest landslides we know, and it starts at around the edge of the gas hydrate stability field. Hydrate clogs pipelines as well as other things. If you remember the Macondo well blowout, they decided that one clever idea would be to put this containment dome over it and pull all the oil and gas up from that containment dome. And so the first thing that happened is the containment dome filled up with gas hydrate and got plugged, which could have been predictable. But and for a while, nations with limited conventional resources, such as China and New Zealand and Japan, were interested in producing methane from gas hydrate. Yet, in spite of this importance, it is challenging to quantify gas hydrate volume using seismic methods alone. So I mentioned that the bottom simulating reflector is it's the fizz gas issue. It doesn't take very much free gas at the edge of the stability field to create a very nice reflection, but that doesn't really tell you anything about hydrate in the section above it. gas hydrate and free gas both produce nice reflections, but it's difficult to tell which from which. Polarity is probably the only guide there, unless you start doing inversions guided by well log data. But speaking of well logs, we know that hydrate is electrically resistive. This is, resistivity logs show that. And way back in 1997, Nigel Edwards from the University of Toronto, who's one of the few people in the business of doing marine EM, wrote this concept paper on the idea of using marine EM methods to quantify gas hydrate in the seafloor. And he proposed this time domain system that's dragged on the seafloor behind a pig. Time domain is not particularly well suited to the marine environment. I asked Nigel why he wanted to do time domain, and he said, well, you guys at Scripps are doing frequency domain, so, I might as well do something different. And Nigel systems and a couple of other systems produced by Rob Evans and Katrine Schwallenberg are designed to be dragged on the seafloor, which is problematic if you're working in an area with pipelines and wellheads and things like that. So Karen and I developed this system we called Vulcan, where we tow the receivers above the seafloor behind the transmitter to produce fairly high resolution images. Because we're towing above the seafloor, we can measure the vertical as well as horizontal electric fields, which is helpful for resolution. And with a fair amount of funding from Fugro for a few years, we developed this into a fairly well-oiled system that had real-time telemetry and good quality GPS timing and so on. And we produced some nice results from it. So we've carried out at least half a dozen projects around the world looking at gas hydrate. The first one for Karen Weidermeyer's thesis was hydrate ridge using deployed instruments. But then we moved on to the Vulcan system. On the lower left, you see a basin scale survey of the Santa Cruz Basin off California. And the green hydrate is actually sitting on the edges of the basin where the faults are bringing gas up. And the BSRs are all nicely developed in the middle of the basin, but that's not where the hydrate is. And on the right, you see an image from Walker Ridge in the Gulf of Mexico, where there was a plan to drill the horizons, those dipping horizons around the center of the image. But the EM data suggests that the place to drill really is on that little anticline on the left side, where there's higher saturation of hydrate close to the seafloor. Here's a nice example from my backyard in the San Diego Trough, where there's a known cold seep, methane seep, that was discovered actually by a group of students at Scripps who had some student ship time to play with. And we managed to get a CSEM tow over it. We produce a lovely image right under the seep that extends to the seafloor, right where the seep is. It's unusually high, 20 ohmmeters for a gas hydrate is a fairly high resistivity in practice. We can back out saturation from resistivity using modified Archie's law. And if you do that and work out how much gas is in this thing, you come out with 0.07 trillion cubic feet, which sounds like a lot, but it's only 1% of the gas in the Scarborough reservoir. So apart from the production difficulties, the other problem with gas hydrates is that they're small compared with these conventional gas reservoirs. And then the more recent work was done in the Pegasus Basin off New Zealand, led by then postdoc Peter Canberg. And we were scaling up the basin scale hydrate characterization, as well as working with Gareth Crutchley to help demonstrate his models of hydrate production in the area. And we collected about 500 kilometers of Vulcan tow right at the middle of the pandemic. we managed to get 4 people into New Zealand under essential worker status. So it was a challenging data collection, but got some really nice results. So on the Glendale Ridge, we see these lovely arcing structures of resistivity in the seafloor, which look amazingly similar to some hydrate migration models developed by Kroger. And they also support Gareth Crutchley's model for hydrate in landward dipping beds as the sediments accumulate and erode and the hydrate migrates. This is my favorite image. This is parallel to the same area, and this is resistivity overlaid on seismic reflectivity. And you can see these lovely fingers of hydrate and gas coming up above the BSR. One of them reaches the seafloor in an area of known seeps, and the coincidence of the seismic reflectivity and the resistivity is satisfying from the point of view of both methods. And we're starting work on using seismic velocities and resistivities to jointly characterize the gas and hydrate concentrations. Groundwater and permafrost have been recent applications for the surface towed system. You've probably heard about Eric's work off Hawaii. We've also done some work off San Diego in the San Diego aquifer. Here's a picture of the system. Again, it's designed to work off small boats. It uses a small transmitter, but even that can produce 100 amps, and surface floating receivers. And this is work that Eric did off Hawaii, where he saw these stacked layers of aquifers trapped by volcanic ash layers, which sort of made people rethink what the hydrology of these volcanic islands would look like. This is some work off San Diego, this done by Roz King, then a student of mine, and Gillian Maloney's. Gillian had worked on acoustics and had discovered these paleo channels offshore San Diego. And we assumed that the groundwater would be in the paleo channels, but when Roz collected the data, they discovered that the paleo channels were actually acting as caps to the aquifer. And furthermore, the aquifers were clearly fault bounded. And this is important because the onshore, the aquifer is part of the water management system of San Diego. And the fact that they're fault bounded suggests that there is little communication between the onshore aquifer and the offshore aquifer, which is important when you're worried about things like saltwater intrusion. Back to hydrocarbons, there are oil seeps in Santa Barbara area. They're interesting beasts. They move around in time. So it's sort of tiresome to keep diving down and try and find out where they are, but they make good targets for shallow water EM. And we produced a nice little paper on looking at the electromagnetic signature of these targets. Roz originally wanted to work in marine archaeology and try and find shell middens with EM. These things are only meters in size, and so we had to push the resolution up. So we've developed a prototype instrument that scales down the source receiver offsets, increases the frequencies, and is designed to tow almost at the seafloor. And this is a first result where in the bottom figure, we have the surface towed porpoise image. And in the top figure, we have the image from the higher resolution system. And they both cross over the Santa Rosa Island fault. And you can see the image of the fault is much clearer in the high resolution system. And so we're trying to sell this idea for geotechnical work in characterizing foundations for offshore wind farms. There's some other work where we show we can recover porosities of the seafloor to within 1% or so using this method. Plate margins were the original target for marine CSEM. Chip's first measurement was on a mid-ocean ridge. The opposite to mid-ocean ridges are the convergent margins. This is a picture from Salmon Ace PhD work, and it's a beautiful CSEM image showing how water is being carried down a subduction zone, not only in the sediments, but also in reactivated normal faults in the crust. The water in the faults doubles the amount of water going down into the mantle than you predict from sediments alone. The other margin, the ridges, I already talked about that central image that was at the East Pacific Rise. I'll talk about some work on the Mid-Atlantic Ridge, which is more recent and interesting. This was a collaboration with Kate Reichert and Nick Harmon from then the University of Southampton, where we co-located magnetotelluric instruments with OBSs. The OBSs had to be left down a year, so we left our MT instruments down a year, and we were only able to collect 3 months of data on our batteries, but that's plenty enough for MT. So this was the first truly integrated seismic EM study of this type. And the results were really satisfying. The colored images are the resistivity from 2 lines, one north and one south of the chain fracture zone. And the one north shows upwelling blobs of magma. The one south shows magma trapped at the base of the lithosphere at a freezing horizon. And the black contours are seismic S-wave velocity inversions, and the purple lines are Kate Reichert's receiver function signatures. And there's really quite good agreement between the seismics and the EM, which made us think, well, you know, it's a standard rock physics trick to use well-logged data to do cross plots of resistivity and seismic velocities. We didn't have well logs, but we had images of both resistivity and seismic velocity. And so we pulled out a first order relationship between velocity and resistivity. And then we predicted velocity from the resistivity inversions. So on the top, you see the velocity inversions using the standard one-dimensional starting model that I showed you in the first slide. And in the bottom are velocity inversions where the starting model was predicted from MT. And they are dramatically different, but they fit the data equally well. And you can see these inversions actually do depend on the starting model quite a lot. And you can see the one-dimensional imprint in the top image, but in fact the asthenosphere is dipping in this area, and it's not necessarily the best model. And with improved coincident seismic velocities and resistivity, we can then start to predict melt, water content, and temperature for this area. The water contents are a little higher than you'd expect, but we think there might be something like CO2 or even sulfides increasing the conductivity of the melt over just water. So this was a great example of how coincident use of seismics and EM can get to rock properties in a much more effective way. And to finish up, I'll talk about some work that I haven't yet published, I'm still working on. When we collected MT data of the East Pacific Rise in 2004 and produced this lovely image of upwelling magma, we also deployed my CSEM transmitter for the first time and collected some CSEM data, which I now finally got around to working on. Here's the inversion of the CSEM data. Looks better when you draw, taking a leaf out of the seismologist book, you draw some lines to draw your attention to things. We see hydrothermal circulation that's limited to layer 2A, the extrusives near the surface, but also stopping at around 13 kilometers away from the ridge axis, where it looks as though the circulation is extending into the deeper crust. And this is consistent with some work that Jeff Gee's group did with magnetics at Scripps. The melt appears to be divided into deeper melt at the base of the crust, and then a shallower reservoir underneath the axial magma chamber. And this is consistent with ophiolite studies where you see foliated basalts at the bottom of the structure. Lead basalts, lead gabbros at the bottom of the crust, and foliated gabbros near the magma chamber. And so we can actually turn conductivity into melt fraction, and we see about 250,000 years of crustal formation stored as melt, or about 14 kilometers of crust. Again, clearly divided into two areas with presumably intermittent hydrofracturing to connect the two. So that's it. You can do pretty well anything you want with marine EM nowadays. That's a green flash taken in the Gulf of Mexico during one of the hydrate cruises. Thank you.
Thank you, Steve, for showing us the evolution of marine EM from the early days until now. Any questions?
Thanks for your talk, Steve. I was actually really surprised by the presence of this low resistivity anomaly at the base of the lithosphere in the equatorial Atlantic. Simply because with seismic methods, we have very few images of a mid-Atlantic magma center at all. And here you show it to persist over a few degrees longitude, which I assume is a few hundred kilometers. So I was wondering, is it even related to mantle upwelling, or is it something that's much more ubiquitous in the equatorial Atlantic seafloor?
Yeah, so it goes out to nearly 80 million years. So it's fairly persistent over time. Is it ubiquitous? I mean, I think that this is a slow spreading center. You see the image from the fast spreading center. It's coming up right under the ridge. This is probably more percolation. I mean, it looks as though it's stopping at the freezing horizon. Certainly, I forgot to mention this image of the EPR. The dotted line tent is Norm Sleep's conductive cooling horizon, 1200 degrees. So it does look as though melt will percolate up to a freezing horizon. Does it eventually freeze out completely? Does percolation stop? I don't know, but in Samanaf's work on the Nicaraguan subduction zone, we also see a conductor at the lithosphere-asthenosphere boundary. We don't have enough data to say, is it ubiquitous? My guess is it is. And my instruments and techs are at sea right now in the middle of the Pacific, trying to find the origin of the Haxby gravity roll lineaments, which may be associated with melting in the mantle. So we'll have a little more data in a few months' time. EM induction is spooky. I mean, it took me years to believe I was collecting real data. And it wasn't until we started getting the agreement with other methods that I had the confidence that we were actually doing something right. And, if you look at the compatibility of the seismic surface wave data and the receiver function data, it's pretty clear that we're all measuring the same thing, and it is melt, which is good because we had to do some fancy tricks to get those images out of the MT. It wasn't straightforward because of the coast effect. The Atlantic is a more difficult place to work than the Pacific because the Pacific has got these subduction zones which channel currents into the mantle, whereas the Atlantic, you see the coastlines all the way across the Atlantic. So technically, we had to do some things that I was uncomfortable doing, but the agreement with the seismics made me feel that, okay, you know, we did the right thing.
Hi, I'm a person who's quite interested in brines, and you're mentioning that you can do brine identification. I'm wondering, what can you tell about the brines? Like, how much resolution can you get on maybe the conductivity or the solidity of those brines? Have you looked at any like hypersaline systems, and what kind of effects have you seen using EM methods?
Yeah, well, brines have a big conductivity signature. You do have three things that'll affect conductivity in a aqueous system. You've got the salinity of the fluids, you've got the porosity of the formation, and then you've got the temperature. The temperature will, you know, drive the conductivity up as well, and up to a maximum. Once you get to the triple point, the conductivity goes down again. The conductivity is pretty well, to a first order, linear with salinity. The most fresh water in the geological environment, in my experience, never gets more resistive than 100 ohm meters. Seawater conductivity is 0.3 ohm meters, so you've already got 2 orders of magnitude there. And then if you go to hot brines in a hydrothermal system, you could get down to 0.03 ohm meters. So there's a large signal to be had there, but you do, you know, to quantify things, you have to control temperature and porosity in some way. Behind you. I like this, tossing the cube.
Nice, thank you. Great presentation. Thank you so much. So we have done some CSEM surveys at the Devine test site for fractured media, hydraulically fractured, and the sandpack is electrically conductive. So we observed some streaming potential signal using CSEM. I was wondering if you have done any dynamic flow monitoring using CSEM in your previous research?
Streaming potentials. The only streaming potential data I have is the Okinawa Trough self-potential, where the self-potential signal is either streaming potentials associated with hydrothermal flow, or the so-called geobattery associated with conductors spanning redox horizons in the seafloor, or a combination of two. Interestingly enough, when we first started towing instruments through the seawater, everybody told me that we would be seeing streaming potentials, and we do not. So our electrodes do not create streaming potentials when we tow them through seawater. So I think the issue of streaming potentials is probably very different on the seafloor than it is on land.
We have a question in the chat.
Yes, thank you very much for a wonderful talk.
All right, we have a question from the chat from Mohsen Amhadian. Great talk, given the carbon storage hubs that are being contemplated in Gulf Coast and resolution of detection of MT and CSEM you discussed, and battery life for the subsea receivers. Please comment on the practicality of use, the EM technology for monitoring leakage in an offshore CCS project.
Okay, well, lovely question. Laura Stern and I just recently published a concept paper on this in the journal Energies. That's an MPDI journal, and I really regret publishing it because they've been spamming me ever since. It's a somewhat predatory organization, I must admit. But we did show that there are CSEM signals, measurable CSEM signals to be had from CO2 sequestration. Laura and I have also measured the electrical conductivity of CO2 hydrate with a view to the idea that if you do get leakage from a CO2 storage system in the marine environment, you could end up creating your own cap rock through CO2 hydrate. So we've quantified, there's actually an order of magnitude difference between the conductivity of CO2 hydrate and methane hydrate, which is quite interesting. It's a different conduction mechanism. And with another hat, I do a little bit of mineral physics. And so that was a fun project to work on. I think you probably would want cabled systems rather than battery deployed, redeployed systems. Navigation is a big issue for CSEM. And so one of the challenges for time-lapse or 4D studies is reproducing the same measurement locations. I mean, even on land, this is an issue. I think MT is useful for controlling the background resistivities, but the signals you want to see are going to be in the CSEM data, not MT. So I think it's I think it's a worthwhile method. I mean, it's also would be good for conventional hydrocarbon production monitoring. And Arnie Orange and I wrote a concept paper on that many years ago that has been extremely well cited, but I've never been able to convince industry to actually collect the data. Yeah, I think it's a viable method, but we're going to have to get some buy-in from the people in charge.
Okay, maybe one more question before we wrap up.
Thanks for the great presentation. And I'm interested in permafrost. So I want to ask if you can use this method to estimate the ice saturation distribution and how accurate it will be.
Oh, well, nice question. You should go talk to the lady behind you. Yeah, and we've done one survey on permafrost. It was pretty successful. We can show where the top and base of permafrost is. In principle, we could get saturation, but I think that's going to take some work. One of the things we discovered was the strongest permafrost signature wasn't its resistivity, it was its resistivity anisotropy. And it was a fairly highly anisotropic structure. And I think it's associated with, as you freeze water, you exclude the salts. And so we think you're getting stacked horizons of ice and brine associated with the formation of permafrost, which will be bound by the stratigraphy of the sediment size. That image of the hydrate in the Del Mar seep, I suppressed it, but that's highly anisotropic as well. And I think we're getting the same sort of thing with hydrate production, also excludes salt. And so I think you tend to get these very anisotropic structures when you freeze water in the marine environment. It gives us data that the seismologists can't always get. And so I think our permafrost work was really very successful, but we've struggled to get the community to pick up on it. We wrote several proposals to do some more work, and the polar community is a little cliquey, and I'm not a card-carrying polar person. So, but I think, I mean, EM has been used on land. Time domain EM has been used on land for permafrost. You get a good signal from it. It's a nice resistor. But Dallas will tell you more.
Thank you.
Well, thank you, everyone. It's 11:40, so I think we'll wrap up. Let's all thank again Professor Constable coming all the way from San Diego to visit us. And enjoy lunch.